Hello, everyone. All right, happy Monday, Thursday, as it is. We are finishing up the alternating series test, and today we are going to finish the module 7. The last thing we were working on with the alternating series test was one, defining what the test looked like. And so here was the test, the alternating series test. We had to satisfy 3 conditions. The first condition is that the terms that are not included in the alternating part, that is the UN, have to be positive. Then the UN have to be greater than or equal to UN plus 1. In other words, it must be a decreasing sequence of terms that are added up to create the series. And then the limit of each term UN has to be 0. We did a couple of examples. We showed that this example did converge by the alternating series test. And then we went on to show that this example did not converge by the alternating series test. And then we went on, and this one we used the fact that we wrote a function called 10x over x plus 1 here. And we took the derivative of the test, showed that the derivative of the function, showed that the derivative of the function was negative, which meant we had a decreasing sequence of terms. And then we went on to show the limit went to 0. And so therefore, this one converged by the alternating series test. Then I did test number 9, which was the test for absolute convergence. That says if I look at the sum of the series with the absolute value terms, and that converges, then the original series I was looking at converges. And so the first example we did was the sum minus 1 to the n over n squared. Our UN was 1 over n squared. We used the alternating series test to show that that actually converges. But we then went on to see what are we going to do in terms of absolute convergence. So we looked at the sum of the absolute value of the terms. We got a P series. P was 2, which meant it converged. So if this series converged, then the absolute value of the series converges, then the absolute value of these terms in that series converged. And so that series converged absolutely. So by showing this, we showed this, and then we showed that. Okay. Then we did this one, which I threw in there because this one didn't have minus 1 to the n, but it does oscillate back and forth. And so therefore I was able to use the absolute value again and do the test for absolute convergence. I got a P series. It was less than 1 over n to the 4th. So therefore the absolute value terms converged, which meant the original series converged. Okay. And then the last thing we were doing was we were looking at this series, which looks like the harmonic series, but it's not, it's an alternating series. And we showed already that this test converged by the test for alternating series. Then we did the test for absolute convergence, and lo and behold, we found out that when you take the absolute value of these terms, you get the harmonic series, which we know does not converge. So this test showed that this series does not converge absolutely. And we were just getting ready to do this last bit. Oh, I am right there. Okay, so the test for conditional convergence. So the test for conditional convergence, this is test number 10. And it says, after you do the alternating series test, you can test to see if the series converges absolutely. A series that converges but is not absolutely convergent is conditionally convergent. Okay. So that therein lies our last test, our last series test, which is this one over back here. And so we know, so what do we know from this series? Okay, so we know this series converges by the alternating series test. We also know the series is not absolutely convergent by the test absolute convergence. So therefore, we don't even really have to apply the last one as a test. We can just say, hence this series converges. Okay. All righty. Have another example. So here's this series. All right, so okay, we can show, well, I'll say you can show that this series converges by the series test, okay? It's the terms UN is 1 over n cubed plus 5. They're all positive. It's a decreasing series and the limit goes to 0. So you can show that this series converges by the alternating series test. And so if we look at the absolute value of this series, we get the sum n equals 1 to infinity of the absolute value of an would give you the sum n equals 1 to infinity of 1 over n cubed plus 5. Okay, so you can show this series converges by the limit comparison test. Okay, and so for us, we'll use Bn will equal 1 over n cubed plus 5. Okay, so Bn, our new series, will be that. Okay, so that's things going to converge by the limit comparison test. So what can we say about the original series? Does it converge absolutely or conditionally? I took the original series, showed it converged by the alternating series test. I took the absolute value of the series and showed that it converged when I used the limit comparison test compared to Bn equal to 1 over up. That should just be n cubed. Okay. All right. So the fact that the absolute values converge, we can conclude that the original series not conditional, because its absolute value converges. Okay. So there's one last part to this section, and that is the alternating series estimation theorem. Okay, so here's the alternating series estimation theorem. It's actually really cool. I like this. It says, consider a series that we already know is convergent. So it's the alternating series. We already know it converges. Then it's of this form. Then we can compute the nth partial sum of this series. All right, so up to n. And that will be such a good approximation to the true value of the series that its error will be less than the next term. Okay, so of course, if I just leave it like that, it's not real applicable, but let's try an example. And here's my example. I'll give you a few seconds to copy that down. I think I went too fast and I don't want to, I'm not trying to rush. I just want you to get it, so. Okay, so we already know the series converges. So if it converges, that means sometimes we can find the sum. Which two series can we always find the sum if they're convergent? Which two series?
Geometric and telescoping.
Good. Okay. All right. So we can actually get an approximation to an alternating series if it's convergent. Okay. And this is how we do it. So let's find S9. Okay. So this is the series that I want to do. All right. So the fact that I'm even asking you to give me an estimate of the sum of the series means I know the series converges. I can't ask you to give me an estimate of something that diverges. So I know it converges. Okay, so this is actually can be written as the sum n equals 1 to infinity of -1/2 to the n minus 1. So I ask you right now, what kind of series is that?
Geometric.
Okay, so that is a geometric series. Good. What is A? And what is R?
Is A -1/2?
Okay, that's R.
Oh,
So R is the thing that gets raised to the n minus 1, and A is the number in front of that, which is 1. Okay, so A is 1, and R is what gets raised to the n minus 1. And in order for this to converge, what is the criteria for that to be a convergent series? Geometric. The geometric series converges under what condition? Whoa, y'all should be screaming that answer. The absolute value of R has to be less than 1. Okay, so the absolute value of R is less than 1, that converges. Okay, so I'm going to compute S9. So S9 says, I need you to add up the first 9 terms. So when n is 0, I just get 1. And when n is 2, no, I'm sorry, when n is 1, n is not 0. When n is 1, I just get -1/2 to the 0 power, which is 1. That's what I was trying to say. When n is 2, I get -1/2. When n is 3, I get +1/4. When n is 4, I get -1/8. When n is 5, I get plus 1 over 16. So I get 0, 2, 4, 8, 16. Good. When n is 1, 2, 3, 4, 5, 6, I get negative 1 over 32. When n is 7, I get positive 1 over 64. And when n is, I'm confused, 1, 2, 3, 4, 5, 6, 7, 8, I get negative 1 over 128. And the ninth term is plus 1 over 256. Okay, there we go. All right, I think I'm done. All right, so that is the sum of the first 9 terms. Okay. And that equals 0.668. So that is an estimate of what the true sum of the whole series, if I summed it to infinity, that's an estimate of what the value of the series is. Okay, so now the theorem, let's go back. The theorem says compute the next term. All right, so the next term is un plus 1. So I am going to compute u10. I'm sorry, that should say S10. That is wrong. I want to compute u10. Here we go. Okay, so I want to compute u10. And u10 is simply going to be negative 1 over 512. And that is negative 0.002. Okay, so the theorem says that the difference between the true value, difference meaning absolute value, between the true value and my estimated value has to be less than the absolute value of the next term. All right, so the true value of the series is going to be S. The nth partial sum or the ninth partial sum we already know is 0.0668. And then the error in absolute value is going to be 0.002. Okay, so that means I'm going to get the absolute value of S minus S9. Oh, let me put in S9. Well, I'm gonna leave it like that for a minute. Is less than the absolute value or 0.002. So now I get S minus S9 is less than 0.002, but it has to be greater than negative 0.002. Okay, so that's what I mean by the distance or absolute value. So therefore, the true value of the series S is less than S9 plus 0.002, and it's greater than S9 minus 0.002. So now I'm going to get 0.668 minus 0.002 is less than the true sum of the series, and that's less than 0.668 plus 0.002. And so now I have a bound or an estimate for the sum of the true series. So this is 0.666 is less than S is less than 0.670. So now I know the sum of the series is between 0.666 and 0.67. Wow, that's not a big range. Okay, that really is not a big range to determine to be off. So let's compute the true value of the series. We said it's a geometric series, so let's compute the true value. So let's compute S. And if it's a geometric series, what does it sum to? Wow. Come on, guys. What does a geometric series sum to? When it sums, it has a certain value. What is it? You got to be able to compute the sum of a geometric series on the test. This is A over 1 minus R. So the true value of the series is 1 over 1 minus a negative 1/2. And that comes out to be 2/3. Remember, 2/3 is roughly 0.667. All right, so it fits right up in the middle of there. All right, so 2/3 fits right in the middle. So that's a really good estimate for the sum of the series. Okay, any questions about this, the alternating series test, the test for absolute convergence, the test for conditional convergence, or the alternating series estimation theorem? Alrighty, that is the end of that section.